Alright, we're going to take a little look-see here at the relationship between Ka and Kb. So what we have set up right here are two different reactions. This one up here is a general base reaction, so NH3 reacts with water to produce ammonium and hydroxide. So we know that this is a basic reaction because it produces those hydroxides right there in the solution. But if we remember, looking back to Bronsted-Lowry, so what's going on here is the NH3 is getting a proton donated to it from the water, and that's what makes it a base. And then over on this side, what we have is NH4, and NH4 is going to be a conjugate acid. So if we isolate that conjugate acid, if we take a look at just that guy right there, the NH4, and we look at it in its own reaction. So NH4 itself, since it is an acid, it can ionize, and it will ionize an NH3 and H+. You can also write this exact same reaction, NH4 plus water at equilibrium with NH3 plus H3O+. Just remembering that H plus and H3O plus are the exact same thing. So both of these reactions indicate the same thing. This one just does a better job of showing the Bronsted-Lowry of the base being transferred, and that's NH4 plus. The proton being transferred over to the water, making this a conjugate acid. So then what we need to see here then, this is the top reaction is a base reaction, and this one down here is the reaction for this base's conjugate acid. So let's play around with the numbers a little bit, and I'm going to show you kind of a little trick that goes along with this. So the Kb, the equilibrium constant for this top reaction, and it's Kb as opposed to Ka because this is a basic reaction. So Kb would equal the concentration of ammonium, NH4+, times the concentration of hydroxide, all of that divided by the concentration of ammonia. We leave out the water because the water, of course, is a pure liquid, so it's not factored into the Kb. And the value of that at 25 degrees Celsius is 1.8 times 10 to the negative fifth. On the other hand, if we take a look at the Ka down here, so this acidic reaction, Ka, and it's Ka as opposed to Kb because this is an acidic reaction. So Ka would equal the concentration of H+ times the concentration of NH3 ammonia divided by the concentration of NH4+. And the value for this one, even though these reactions do look similar, this is the base and this is its conjugate acid, the value for Ka for this reaction will not be the same. Instead, it's going to be 5.6 times 10 to the negative 10th. So a couple of things I want to point out with this. The first one is, even though this reaction down here just appears to be this one flipped for the most part, this value right here does not indicate that. This value down here shows that both of these two reactions favor the product side. Alright, if we were just flipping this reaction, then it should flip this to a positive number, but since they're both negative, it means both of these reactions favor the reactant side. So they favor this side, the left side of the reaction. These do both have the same compound in it, molecule, NH4+, so there is a relationship between these two values, and that's what we're going to take a look at here. So the relationship between Ka and Kb. To do this, let's actually take Ka and multiply it by Kb. So we're going to multiply Ka and Kb. Let's just use the variables in here so I can show you something. So Ka was the concentration of ammonia, NH3, times the concentration of the proton, H+, divided by the concentration of ammonium. Alright, just taking these from the previous screen. We're going to multiply that by the Kb. So Kb was the concentration of NH4 plus times the concentration of OH minus, all divided by the concentration of NH3. So then if we take a look at these two, when we multiply Ka times Kb, what do you know? NH3, that'll cancel out NH3. NH4, that's going to cancel out NH4. So what we're left with when we multiply Ka times Kb, back to my other color, so Ka times Kb is equal to the concentration of H plus times the concentration of OH minus. And what is the concentration of H plus times the concentration of OH minus? Why, it is the Kw, the equilibrium constant of water. So what this means, to clear our boards and try again, Kw is equal to Ka times Kb. And we always know that the Kw value at 25 degrees Celsius, so I shouldn't say always, is 1.0 times 10 to the negative 14th. What this means is that with any Ka or Kb, we can calculate what its counterpart is. So if we know the Ka of a weak acid, we can find the Kb of its conjugate base using this little fact right here. We're never going to use it really to find the Kw, because Kw, it's always the same thing. It's 1.0 times 10 to the negative 14th at 25 degrees Celsius. We're going to use this little idea right here to find either Ka or Kb. Let's take, for example, formic acid. So formic acid, HCOOH. This is the acid that's found in bee stings and ant bites, so it does burn pretty good. It ionizes, it's a weak acid though, so it ionizes into H plus and formate COOH minus. So in this case, our weak acid would be the formic acid right there, and its conjugate base would be COOH minus. So the Ka for this reaction right here is, and we can get this from our textbook on page 612, 1.7 times 10 to the negative 4th. So let's say I asked you to find the equilibrium constant for its conjugate base. So the conjugate base for formic acid, I've already said, is going to be this guy right here. And so when it reacts, it's going to be COOH minus, and it's going to ionize with water. And so it will take a proton away from water to become HCOOH again and produce those OH minuses. So we can see that this is a basic reaction because of that hydroxide, and so we want to find the Kb for that guy. So the Kb for this reaction, for the one up here on top, we would get that by using this relationship right here. So we've got the Ka, we know the equilibrium constant for water, let's find the Kb. So if we just rearrange this, 1.0 times 10 to the negative 14th divided by the Ka value, and the Ka value is the 1.7 times 10 to the negative 14th. That'll give us our Kb, and Kb is 5.9 times 10 to the negative 11th. So what we did here is we used the relationship between Ka and Kb, which forms the Kw. Use that to find the equilibrium constant of a conjugate base. You could do the same thing if we used a weak base. We could find the equilibrium constant for its conjugate acid just by using this relationship right here. Might see this pop up a couple times, but we're going to end up using this a lot when we get to buffering systems and titration. So just kind of commit this to memory. You've got it in your notes. Might pop up on the quiz tomorrow. But just remember this relationship right here once we get to the jumping between acids and their conjugates or bases and their conjugates.